Okay, this video would continue with our lecture in topic 1, differentiating between exothermic and endothermic reaction. So let us look at exothermic reaction first. So exothermic is a reaction whereby the energy is actually released during the bond formation, like what we mentioned in the previous topic over here. So that then the energy released during the bond formation is actually greater than the energy that's absorbed for bond breaking of reactant. So what does this paragraph say exactly? So for example, AA plus BB to form AB and AB. So as you know that the reaction does not form just like that. So from the reaction mechanism, what it does is it forms this species over here where the bond break, and for B it breaks as well. So you form an individual atoms over here before we proceed over here. So during this part, this bond is break and this bond is going to form. So this is a bond forming process. This is a bond breaking process. Okay, this is bond breaking. So this will have a reaction of bond breaking, have a heat of reaction in the bond breaking. This will have a heat in bond forming. So when you have a bond breaking will absorb energy, a bond breaking will release energy. So a bond breaking, so in an exothermic reaction, the bond breaking value will be higher than a bond forming heat of reaction. Okay, so in this process you are going to have an exothermic reaction. So since this heat of reaction is defined as the energy absorbed during the chemical reaction, so we are talking about the net absorption. So an exothermic reaction will have a negative value, as what we have actually seen in the previous example over there. So and therefore with this, the internal energy of the product will then be lower than that of the reactant. So there is a net drop in terms of its internal energy. That will explain why the heat of reaction is lower than 0. So an endothermic reaction is the direct opposite of an exothermic reaction. So in exothermic reactions, the temperature of the surrounding will actually increases because the reaction release energy into the surrounding. Whereas in endothermic reactions, the energy is absorbed during the bond breaking, and then the energy absorbed for bond breaking is greater than that of an energy released in the bond formation. So all in all, you have a net amount of energy that's being absorbed. So energy is being absorbed from surrounding that cause the temperature of surrounding to drop. So like similarly as previously, heat of reaction is defined as the energy absorbed in a chemical reaction. So an endothermic reaction will have an overall positive heat of reaction. So since energy is absorbed from a reactant, the product will have a internal energy higher than that of the reactant. That's why this difference is the heat of reaction will be more than 0. So for this case, we can actually look at here. For an exothermic reaction, the bond breaking is higher than that of bond breaking. So in a endothermic reaction, the heat of bond breaking will be greater than that of bond forming. So this is endothermic reaction. So let us look at this table over here. They give a overview summary of what we have covered so far on exothermic and endothermic reaction. So over here, the table says that for an exothermic reaction, the standard heat of reactions delta HR will be negative. Delta HR is smaller than 0. So endothermic reaction will be positive. Delta HR more than 0. So about the direction of energy flow, so for an exothermic reaction, it means that the reaction is giving out heat. So heat is a form of energy, so it's given out by the reaction. So it is from the system to surrounding. So an endothermic reaction is the direct opposite, from surrounding to system. So what about, so since for an exothermic reaction, the energy flows from the system to the surrounding. So the temperature of the surrounding will increase because there's a net increase in the surrounding energy, so that converts into temperature. So for this, endothermic will be decreased. So internal energy of the reacting species. So as we mentioned earlier, the energy of the product, we are now looking at the energy of the product and compared to the energy of reactant. So an exothermic reaction, because there is a decrease in the energy because of the energy actually move from the system to the surrounding. So the overall product energy will be lower than that of the reactant because all this excess energy actually went to the surrounding. So in the endothermic reaction, the energy of product will then be greater than that of the energy of reactant. Remember that energies cannot be created nor destroyed. So definitely, if let's say there's a net increase in the energy of the product, so energy must come from somewhere. So what does it come from? It comes from the surrounding to the system. So this is a good overview of this endothermic and exothermic reaction. So now let us look at the next part over here. The standard heat of reaction delta HR for combustion ethanol is negative 1418 kilojoule per mole. So the reaction then proceed with the following like stoichiometry over here. So let us draw the energy diagram for the combustion of ethanol. So the energy diagram we are looking at here. So this is the energy axis in kilojoule per mole. So if for this case the combustion ethanol is negative value, so this over here is an exothermic reaction. So which means to say that the energy of the reactant will be higher than that of the product. So initially C2H5OH plus 3O2 over here. So the the energy of the reactant itself will have a higher energy than that of the product. So there's a net decrease in the overall internal energy. So this 2CO2 plus 3H2O over here. So there's a net decrease in energy. So with this, let us calculate the heat of formation of ethanol. So we know that, let us look at the stoichiometric reaction over here. So the ethanol is actually reacting with 3 molecules of oxygen to give you 2 molecules of CO2 and H2O. So the heat of reaction will be the heat of formation of my product, which is CO2, and there's a stoichiometry of 2, coefficient of 2, so we must include the 2 over here, plus 3 times the heat of formation of water minus the sum of heat of energy, heat of formation of ethanol, plus the heat of formation of oxygen. So we look at here again, that as mentioned previously, that heat of formation of oxygen, which is an element, this should be 0. So you only left with heat of formation ethanol. So we can go ahead and sub in the value. Heat of reaction is negative 1418 kilojoule per mole. So the heat of formation of CO2 is, for CO2 is over here, negative 393.509 kilojoule per mole. For water over here, this is liquid. So let us look for water. The heat of formation of liquid water is negative 285.8. And we minus off the heat of formation of ethanol. So this is the one that we are supposed to find. So you can work out this equation and solve for this heat of formation for ethanol. So you should get a value of negative 226.42 kilojoule per mole.